that computes kilonova light curves, which at the moment it's more or less, I guess, a black box for you in the sense that you know that there are some equations that are implemented, but you don't know exactly which equations. And I also provide some estimates. So now the goal of this half an hour is just to sketch a bit. Okay, but I know that I will take always more, so let's stick at initially on half an hour. But so I will try just to give a justification of the model and why do we expect the time scale that we have. So this is the framework that we had in mind. It connects totally well with what Gabriele discussed, so I don't have to make the introduction about the kilonova. Let's try to see how can we model from a quantitative point of view the kilonova. We have seen that two neutron star collides, there is an ejection of matter. This is what we call the ejecta, and we had characterized this ejecta up to now in terms of average property. For example, what is the average YE, how does it depend on the angle, and in terms of the ejected mass. But actually, this is not a fluid, this is not a big particle that is just flying in space. This is a cloud that is expanding. So we have actually to deal with a distribution. So instead of the scalar quantity that you see here, let's introduce a function that depends potentially on the theta angle, on the phi angle, and also on the velocity. Of course, this is already a rather complicated problem. Let's try to make it simple. As a first approximation, let's assume that the model is isotropic, which means that for the moment we will drop these two quantities. We already know that this is not correct, but as a first step we do isotropic and then we see how to make it anisotropic, okay? So this means that our xi is actually only a function of the velocity. Concerning the velocity, we assume the so-called homologous expansion. The concept of homologous expansion is not new in physics. The expansion of the universe is homologous, especially in the early phase. A core collapse is an homologous collapse. What does homologous mean? Homologous means that somehow, if you have a certain distribution in terms, for example, in the velocity space, and then the system expands, you keep that distribution. You have just a rescaling factor. That's why in the core collapse and in the universe we have exactly these kind of things. So whenever you have an homologous expansion, one of the best way to describe this homologous expansion is to go into the velocity space. So you can think about it. Let's take a picture of the ejecta at a specific time. I just look at the fluid element and I associate it to each of my spherical shell a certain velocity. If you are in the homologous expansion approximation, at every time the same shell will have the same velocity. It will just expand radially. So this means that, as I said, our xi is only a function of velocity, and if you want to fulfill the continuity equation, one of the ways is that it assumes this shape. So there will be a normalization factor, and then 1 minus v over v max squared cubed. So this is the way in which the velocity mass is distributed along in the velocity space. If you make a diagram of that, if this is the velocity, there will be a maximum here. And if we make it linear, of course, here we have xi 0. If we make linear, then we have something like that. Okay? So this means that most of the largest part of the ejecta, it goes with the velocity that it's not the maximum, but there is always a tail that goes to the maximum. Why do we pick up this shape? And the reason is that it fits with what comes out from the simulation. Okay. Once we have introduced this quantity, which tell us how much mass goes with a certain speed, and this is a constant in time, so there is no time dependence, so it's kept constant, we can introduce other quantities. So for example, as I said, what is the average velocity here? We can compute, for example, the root mean squared velocity, which is nothing but the square root of v squared using this distribution, which is simply, well, okay, if you perform the calculation, this means that you go from 0 to v max of our xi function of v times v dv divided by the integral between 0 and v max of xc in dv. By the way, this is nothing but the ejected mass. Yes, thanks. 1/2. By the way, this is nothing but the normalization factor, the ejecta mass, that actually it's another way to give xc 0. We will end up with 1/3 v max. So the bulk of the velocity actually is somewhere here. This is the v root mean square. You can think about it as a characteristic velocity. So we said that dynamical ejecta has a typical ejection velocity of 0.25, if you remember, 0.22 or 0.25. This means that this will be our 0.25 for the dynamical ejecta. And this means that dynamical ejecta has tails that go up to 0.7 c. Okay? But the bulk is 0.25. Okay, so we have this matter. We know how it's described in terms of mathematical sense, how it expands homologously. We know more or less which are the properties. What do we need now for a kilonova? Well, just trying to put in bullets what Gabriel said. First, we need radioactive arc process, radioactive decay, or better, radioactive heating. Then we need thermalization. Then we need diffusion. And finally, we need emission. And this is what will then reach the Earth as a kilonova. Now I will just go through these points here very, very briefly, just to give you a flavor for each of them. Let's start from the radioactive heating. This is a picture that Gabriel showed. I showed a slightly different picture, but it's from the same paper. We know, so let's start from point 1. We have heard that the radioactive heating can be easily parameterized, and you can see from this picture as a constant factor, and then comes the power law dependence that we have. And this alpha coefficient is 1.3. And here you can see how robust is the kind of slope that we get. Because this is very different y, 0.05 up to 0.3, and even with a different mass model, and still you catch up to a factor roughly of 4, this kind of. So the point is that it's too nice not to have a physical explanation, simple physical explanation. And then we search for it. This argument actually goes back to this paper, and probably Gabriel did it, I would say. Okay, so where does this heat originates? It's different from core collapse supernovae, when we know that we have a bunch of nickel that decays to go cobalt and then cobalt to iron. Here we have a broad distribution. If you remember, this is a similar plot, but we have seen already several times. Around one day, we have a bunch of nuclei that are just on the right side of the value of stability and are decaying back to beta through beta decay towards value of stability. So in the end, we have a distribution of nuclei that tends to go decay through beta decays. How can we describe this? Well, the first thing is that, okay, we focus on beta decays. We know that we could characterize a beta decay with its Q value. The other thing that we know is that how does, for beta decay, the Q value compare with the quantity that I define as eta as the neutron excess. What turns out is that Q actually is proportional to the neutron excess. And if you want to get just a simple argument, is that if you neglect, for example, Coulomb interaction, and then you consider an isotopic chain, you will have here the n equals 0, which is the minimum of the chain, and then you will have here the other nuclei. Okay? And this is, of course, +1, and this is -1. So somehow this is eta equals 0, eta equal 1. This is a parabola, and then you can describe the energy per baryon as a constant plus a coefficient times eta squared. Now the Q value is nothing but the difference between 2 points. So ideally what you have to do is to make the derivative, the finite difference between two. And if you make the finite difference of this, you will end up with something that is proportional to eta, because you go from second order to first order. So that's why here I can write them. Moreover, beta decay is a free body decay, so you have initial state going to final state plus electron plus neutrinos. And I think most of you are familiar with the fact that if you just make the integration over the phase space of the of the delta, you end up with something that the decay rate must be proportional to q to the fifth. This is simply phase space argument, which means for us that it's proportional to eta to the fifth. Okay? Now, I said that we don't have one nucleus that it's decaying. We have a bunch of nuclei that are decaying at the same time. What we can say, how many nuclei are decaying? How many cells I have to put? As you can see, the number of cells that we can put once you fix, for example, a certain electron fraction, is roughly constant in terms of eta, because the amount of nuclei that I have in this chart here is equal to the one that it's here, and so on and so forth. So what I can write is that the amount of nuclei that I have per unit of eta is roughly constant. But now I know what is the relationship, because from this one I can deduce that eta goes like lambda to the 1/5. And if I define tau as lambda to the -1, then I can also say that eta is tau to the -1/5, right? So if I start from dn over the eta, just making the differential, taking into account these conversion factors here, it's quite easy to end up with something like that. So I can describe the number of nuclei as a function in terms of in the lambda space, and this becomes a constant times lambda to the -4/5. I can do something similar also for tau. You can also easily do the math. It's not an issue here. The n over the tau. In this case, you end up with something that is equal to a constant times tau to the -6/5. You have just to make, just chain rules for the derivatives, nothing more than that. Okay, so up to now we have only described how the number of nuclei can be expressed in the space of the eta, or in the space of the rates, or in the space of the half-life. Now, let's make a bit an assumption now. Let's assume that at a certain time t, the nuclei that contributes are the ones that have a lifetime of tau, which makes sense, because you produce everything at the beginning, and then if you wait 1 minute, you will see decaying nuclei that have a lifetime of 1 minute. Okay? So, at time t, what is important is to take t equal to tau and see which are the nuclei that are relevant at that time. What is the amount of nuclear heating at that time? E dot. Well, we have to pick up a certain nucleus, a certain Q value, but the heating is somehow proportional to the Q value of that reaction. So I put the label T equal tau to say that it's the specific Q value of the reaction that has a tau equal to T. Then we have to multiply, of course, by the amount of nuclei that decay per unit time. But remember that now we are evaluating this at T equal tau, so I can just pick up this formula. So Q is tau to the -1/5, because Q is proportional to lambda, but tau is just 1 over lambda, so you get just a tau -1/5 times. Now we have the dependency here that I take from there, so it's a tau to the -6/5, again evaluated at t equal tau. If you put everything together, you end up with tau to the -7/5, which at tau becomes t. What is 7/5? 4. It's not exactly 1.3 because this argument is very, somehow it's straightforward. There are some details, and if you take into account these details, it turns out that it has to be slightly smaller than that, but 1.3 is actually slightly smaller. So this is the argument behind the fact that once you have this kind of condition, so a distribution of nuclei that is decaying, that it's not one nucleus, but it's a set of nuclei that statistically is decaying back to stability via beta decay, this argument can be applied. And we have actually verified them in detailed nuclear network calculations. Okay, so this is concerning point 1, what I wanted to say. Gabriel mentioned something about thermalization, and this is very complicated business, so I won't go into that. I want just to show you the result of this paper from Jennifer Barnes and collaborators, and you can see that this is the result that you want to put. So you ask yourself, okay, the nuclear decay produces a certain amount of energy. How much of this energy stays into the matter? Or in other words, how much of this energy I'm not able to thermalize? And you can see here the fraction, it's a dashed line, and it's a quantity that at the beginning is close, you know, this probably is just a neutrino contribution which you lose anyway. And then since the system is expanding, you become more and more difficult to thermalize, and at late time, you are not so efficient. So for example here, only 10% of the energy that it's decaying is actually thermalized locally. This is an important factor. Diffusion. What is diffusion? Diffusion is something, it's a process that tells you that whenever you have a radiation that needs to go through a medium, this radiation cannot escape necessarily freely if there is a certain opacity, okay? We have heard from Gabriel that opacity depends sensitively on the composition. What is the origin of this? It's very simple. And lanthanide and actinide stays here in this table. And you know that this is the periodic table. And the fact that you can put the elements in an ordered way depends on the fact that they fill the same shells. There is an electron shell structure, and the farther you go down from hydrogen to lanthanide and actinides, the more you fill electron shells. This means that especially when these atoms are not fully ionized and you have a lot of shells that are only half filled or totally filled, whenever photons encounter one of these lanthanide and actinides, there are millions of possible interactions that this photon can do with this atom. This means that whenever you start having lanthanide and actinides, the opacity, so the capacity of the photon to interact with the atom increases by at least order of magnitude potentially. Just to give you an idea, if the electron fraction stays below 0.25, then we can prevent the formation of lanthanides, and here, typical optical... above 0.25, we do not produce lanthanides, and then the effective opacity there are of the order of, let's say, between 0.1 and 1 centimeter square per gram. Okay, this is if YE is above 0.25. But as soon as we go above 25, then we start having also this component, and we just said the lanthanides could actually become a contributor to the opacity, and we have already heard that even a decent amount of the order of 10 to the minus 2 could actually lead to opacity of the order 5 to 10 centimeters square per gram. Let's say 0.25, 0.15, YE 0.25. If we get even more neutron rich, we can actually end up with a third process peak and the actinides, and then the opacity, it's of the order of 10, 30 centimeters square per gram. Just a few caveats to all this. This is an effective opacity because every nucleus has its own opacity, but of course we cannot model this at the moment. Moreover, the opacities of those elements are totally unknown, even from a theoretical point of view. There are very, very complicated calculations that are just coming available at the moment, but these are really very few nuclei very few transitions compared. So there is a long way ahead to model this correctly. Yeah. Yes, exactly. So it's also a bit, yes, it's also a bit misleading. It depends also on who you ask. I think that this opacity were very much in favor by the Los Alamos group, while Tanaka, and then so it really depends on the way you treat the lines. So yes, I can put this in bracket and add on the top of that that if you have a mixture of the different channels, you could have something in between. So please keep these things as just some guidelines, but I think nobody really knows apart more detail than that. Okay. Once we have the opacity, how does the opacity enter? I don't have okay. I don't want to enter too much in the details, but the idea is that we have somehow to model the so-called radiative transfer. What does it mean? Let's say there is a concept. Okay, the opacity is somehow a local quantity. It tells you how much matter is opaque with respect to radiation. Okay, there is a quantity that it's slightly more intuitive in some sense. It's called optical depth. The optical depth tau is defined as the path. You can define an optical depth over a certain path gamma, and it's defined as 1 over lambda, and then you make the path integral over this quantity. So you have to imagine this situation. Imagine to have a gas. You get some radiation get into, and you just take a photon that just does a random path and starts to scatter around. Okay, I call gamma this path here, and the optical depth is nothing but one. Okay, what is lambda? Lambda is the main free path. I think I already wrote the definition on the blackboard how to relate lambda with sigma. So the idea is that lambda is 1 over the density of the scattering center times sigma, or if you want, rho kappa. So kappa, if you know also the local density, you know what is the local main free path. What does it mean to take this integral? 1 over lambda integrated over a path tells you how many times a photon interacts. So if I compute the optical depth for this path here, I should put 1, 2, 3, 4, 5, 6, 7, 8. The optical depth along this path for this photon is 8, because it's the number of interaction that the photon does. Okay? The main free path is a quantity that enters all the radiative transfer and all the optical depth as well. I will just give you a flavor of that, in the sense that I will write the simplest possible radiative transfer equation that you can imagine. I can imagine that here I have a certain intensity is 0. I could ask myself how much intensity I have here. Okay? This is a radiative transfer problem. The variation of the intensity in the line of sight, let's call it Z for simplicity. Let's assume this is the Z axis. We could actually locally produce some radiation. This is the so-called emissivity. But we could also absorb some of this radiation, and this is so-called absorptivity. So kappa, rho kappa probably, rho kappa, and it's proportional to the intensity. This is the simplest equation. Let's assume for the moment that all the radiation comes from here, and we simply scatter inside that side. So let's assume to neglect this one. Then once from the definition of lambda, from the definition of the main free path, it's quite straightforward to see that d tau is nothing but k rho dz. Which means that d E is nothing but E d tau. So the variation on the intensity depends on the variation of the optical depth. Now I can easily integrate this equation, and it tells me that E at a certain tau is nothing but E0 exp of minus tau. What does it mean? Here, the optical depth is 0 because the gas is inside. Here, the optical depth is k times rho times, let's call it L, where L is this line here. I'm assuming a uniform kappa and rho inside the gas. So what it's telling me, this quantity here, is simply that if I plot it as a function of tau, well, it does not necessarily end. So what a medium can do is simply to damp the radiation. I enter with a certain amount of radiation, but a fraction of this radiation gets scattered or absorbed, and I lose it and when it exits, because it's either inside here, either outside here. This is simply, you can have this experience if you are in the fog and there is somewhere a sound. You hear much less than when, or even for the light. This is simply the same kind of argument. Yes? Well, we have some information, we don't have precise information.
But, I mean, from experimental point of view, this doesn't seem like a very complicated.
Well, the point is that it's easy if you have stable nuclei, but we are speaking about opacity. No, this is not true, because this is what we need is the opacity at a late time. Mm-hmm. Yes, to measure these transitions. There are billion, they are not exciting. No, it's even a matter of money. To get a decent amount of these lanthanide and actinides costs money to the laboratory. And then you have to consider that you can have excited states, you can have some different ionization state. But depends also how many lines. Of course, it will be great to have a code that can compute them and compare well. So I think what the people now are trying to do is to tune their code, atomic physics code, to reproduce the result that we know, so that we can trust the code and use the code to produce at a mass production scale something. But at the moment, the code does not agree necessarily well with the data. So there is much work to be done there. Okay, so this is the concept of optical depth. From this very schematic picture, you can understand also something else. If the photon could travel fast and straight, the amount of time that it takes for the photon to go from here to here, it's simply L over C. But the fact that the photon is constantly scattering makes him make a much longer path inside. So even if the photon is locally always moving at the speed of light, the effective velocity of the photon is much lower. Well, it's lower depending on how many times it interacts. I don't have time to show, but if you use something like random walk approximation, it's rather simple. I mean, it's a nice exercise, but I think I don't have time. You can easily show that the effective velocity of the photon, it's nothing but c divided by tau. So if you interact only once, then you go at the speed of light, which makes sense, because then you are produced here, you arrive there. If you interact more and more, it takes much longer time, because your velocity becomes small. This is what I wanted to say. So this is the important formula that we need from the diffusion side. Okay. Finally, what I call the emission, from this point here, what I simply want to say is that, I don't know how much you are familiar, but if we have a gas that it's in thermal equilibrium, and we want to know what is the radiation that comes from that gas, this is an old problem that you can find in old quantum mechanics textbook, probably in the first chapter. It's called the black body radiation problem. And this black body radiation problem, it's one of the major results is the so-called Stefan-Boltzmann law, which tell us that if you have a body, whatever shape, complicated you want, but if you pick up a certain surface here and you ask yourself, and the body is at certain temperature T, this emits an electromagnetic radiation such that whatever surface you take, the amount of energy that is emitted, so this is energy per unit surface per unit time, is equal to a constant that is called the Stefan-Boltzmann constant, T to the power of 4. Okay, this is just black body theory. And this we have to keep in mind for the emission. Okay, so these are the 4 points that I want to discuss, and now we have to put everything together to make finally the kilonova model. The idea the idea is this one. We have the merger here, matter expand with a certain homologous expansion law. It was written there before. Let's make something like that. So this is where you have Vmax. Deep inside, so this is our material that it's doing our process first, and then it's is radioactively decaying towards the value of stability. So here there is a lot of nuclear radioactive heating. But if you are deep inside, the matter is going slow, there will be a region where actually the system is opaque, because photons here are still diffusing a lot, okay? And this we call it the opaque core, or optically thick. So now we are fixing the time. We assume that the time is fixed. We make a picture, there will be an opaque core, then there will be here another region where the code is radiating, so photons are produced, but actually they don't scatter too much. I will quantify this too much soon, and it's called the radiative envelope. The radiative envelope is defined as the region where this surface here is what actually defines the radiative envelope, is defined as the region where the velocity of the material equal the effective velocity of the photons. Okay? So the idea is that a photon here has still to diffuse, but it will diffuse on the same time scale as the material expand. So it will become material will become transparent within a few scattering processes. Okay. We thought that thermalization is important, so if you go too far away, there will be a point where the optical depth becomes less than 1, and then you cannot thermalize. Then here there is a region. This is what is called the photosphere. The photosphere is defined as the point where the optical depth becomes 2/3. Okay? So the core is opaque. There will be nuclear heating, but it's hidden inside. We need to expand it. This is the radiative envelope where the expansion is, matter is getting transparent, and the photons that are produced there will actually leave the system, and then there will be a region where the photons will actually leave the system that is called the photosphere. How do we translate this on a quantitative basis? Let's start from this expression here. Velocity equal to c, do you remember, over tau, because the effective velocity is this expression here. How do we estimate tau? Tau is just the optical depth of this shell here. So this is its rho, an average rho of this region here, times delta r times kappa. If you remember the definition of optical depth that I gave, this is, of course, we do something like that. What is the average rho here? The average rho is nothing but the mass that it's above this region here. So I call it m greater than v, and that's a function of v, times delta r divided by 4 pi v square t square. kappa. Okay, so kappa and rho, they are there. I just estimate the density, like what is the mass that is contained inside this shell divided by 4 pi v squared delta t squared, delta r. So this is just the volume of a shell. So it's the mass inside this shell divided by its volume. The good point of this approximation is that it's independent from delta r, and so we end up with m greater than v times kappa divided by 4 pi v times t. And on the right-hand side, I have v. I forgot before to introduce this quantity here, but if you remember, it's easy to understand. Actually, I draw v and the enclosed mass. So I can always define my m greater than v. It's nothing but the integral between v and v max of my distribution xv in dv. It's simple, this. So this is xc. You remember I did a plot like that, and this was v max. I can always fix a velocity and count how much mass is larger than that. This will be the mass that is outside this shell. Okay, sorry, I forgot to introduce before. This relation here gives you the possibility, given a certain time, to know what is the velocity of the shell at which matter become radiative relevant. So let's call it radiative. If I do the same game for the photosphere, so I can always do the same for the photosphere. Let me see. So let me check if the formula is correct. C over... No? There is a C missing. Ah, yeah, because I put tau on this side. Yes, sorry. So this is C. Because I put tau on this side, and then there should be... Okay, so I put tau on this side, I put V on the other side, and the formula becomes this. Okay? So if I fix a certain time, I know what is the velocity of the shell where matter starts to become, from the radioactive point of view, interesting, because things that emit there will be, decay there will be emitted. I can do the same game now with the photosphere. I can solve this equation here again, but putting t tau equal to third. This is maybe a detail that I could have skipped. It's 2/3. So I can just rewrite, if you remember tau, we had this expression here for tau, so it's the density divided by 4 pi Vt squared delta r, then we have delta r times kappa. I can always put to 2/3. And this equation tells me what is the velocity of the photosphere at a given tau, t, sorry. So at a certain time, I can compute what is the velocity of the here, what is called v rad, and what is the velocity here, which is v phot. What can we say about v rad with respect to v phot? Which is larger of the two? Look at the picture, look here. It's homologous expansion. The things that are faster are the ones that are farther away. What is farther away, the photosphere or the radiative radius? The photosphere. Okay, so we have this formula here, and then for a given time, we can actually get the velocity corresponding to the two. Now, we are almost at the end. How do we know how much luminosity is powering our kilonova? The luminosity that comes into photon for the kilonova is nothing but the nuclear energy at time t. We know that only a fraction of this energy actually becomes available for the kilonova, so we have to multiply by the thermalization coefficient. This is all a function of time. But this is energy per unit gram. We need to know how much mass is decaying at that time. And this mass is actually the mass that is contained between these two spheres. So it's the mass for V rad minus the mass greater than V for V photon. So I have to cut only this mass contribute because this one cannot thermalize. So I just need to know what is the mass inside here, which is nothing but the difference between the mass at the photosphere velocity and the radiation velocity. But I have everything because everything is on the blackboard. Because this, we know that it's E0 t over t0 to the minus 1.3. This is something of the order of let's say 0.3. We have seen that it's a function of time. And now we can, for each time, we can compute these two quantities, and then we can get our light curve. So the idea is from the time, we get V rad and V phot. From this we have the two masses. From the time we get also the heating rate. And we have also the thermalization factor. And so we can compute the luminosity as a function of time. Moreover, we know that this emits as a black body. This is per unit surface, but we have a sphere. We know what is the radius that it's emitting. It's the temperature so the Stefan-Boltzmann law was J sigma Stefan-Boltzmann t to the fourth, but in our case J is nothing but luminosity divided by 4 pi. What is the radius? It's the radius of the photosphere. So it's V photosphere times t squared. If you can invert this equation here for t, and becomes simply luminosity divided by 4 pi Stefan-Boltzmann V photosphere 1/4. Okay, so we know the luminosity as a function of time, we know the temperature as a function of time, we know the radius of the photosphere as a function of time. It's simply V phot times t. This is our basic kilonova model. If we know these things here, you could compute the broadband light curve and things like that. This is actually done in the code that I gave you. So the code that I gave you, it's just the solution of this problem done in Python. I forgot to mention that I wrote the first version of that code, and then Walter Del Pozzo, who is now at ENFN of Pisa, helped me rewriting in a decent Python. So the version that you have, a good fraction of the credit goes also to Walter that helped me optimizing, and it's 30 times faster than my first version that was not in Python. Well, written in Python, but not Python-like. Okay, this is something that I don't need to mention because Gabriel did. So there is this red or blue, depends 1 day, 1 week, blah, blah, blah. We have seen both this component, and this has an impact. What we did, actually, the code that I gave you was used to make some publication. And the publication that we did, we tried to put everything together in the sense that we know from simulation that there is dynamic ejecta, there is wind ejecta, and there is a viscous ejecta. We know that the dynamic ejecta has a larger YE, and so it's less opaque. That's why I make it color blue, while on the equator we have a color red. This is an intermediate color. And then we put everything. This is the way in which, by the way, this is a spherically symmetric model. I told you that kilonova is not a spherically symmetric thing. So how did we go from something spherically symmetric? We just discretize the angle in several bins, and within each bin we solve a 1D problem. Okay, that's why it's important to make first a spherically symmetric case, because then you make a lot of spherically symmetric problems. We did it, and we were able, you can see the points and the lines, and they agree quite decently. We were not the only one doing this job. Of course, there are other people making better figure, I must say, like Villar et al., but work from Tanvir, Tanaka, and Dankesen, where they also could fit. What is the take-home argument? So what can I say? What is robust from this observation? What does this observation tell us? To me, and this is the last thing that closes the school, don't worry, it's there has been probably a certain ejection of matter. If you sum all the components, you need something of the order of 0.05 solar masses. So we need dynamic ejecta, but that's small, 10 to the minus 3. We need ejecta from the disk. So the disk ejecta is really, as Gabriel said, probably the dominant component. We had the blue component, which to me it simply means that neutrino matters. Because you cannot have a blue component if you don't reset YE through neutrino interaction. And the third thing is that the fact that now the model is anisotropic gave us the possibility to fit also the angle, and the angle that we got is 30 degrees, which agree very, very well with the gravitational wave signal, even if they are totally independent signal. So we got an independent confirmation that the angle was 30 degrees. And then the fourth thing is that, I mean, I don't write it, but I think it's good because we could say that we really understand what's going on, and for me it's impressive. So when this kilonova happened, dinosaurs was on the Earth, because this object is 40 megaparsec away, and this translates roughly into 120 million years. So when the dinosaurs were just on the Earth, a kilonova exploded in a nearby galaxy from the collision of two objects that has 10 kilometers radius. So it's smaller than any decent town on the Earth. And now, several years after, on a small planet, just detecting tiny 10 to the minus 20 variation in the path of a photon in a laser, and putting our telescope, we are able to say how much mass was ejected, how was its composition, what was the mass of the neutron star. So I think this is really amazing, and shows really the power that we have in understanding the universe. But this is only the beginning, in the sense that our models are still very crude, very simple, and I think there is a long way to go. Lunch.